All right, we are live. So it is my absolute pleasure to introduce Gavin Uberti, who's here to speak with us today. Gavin is CEO of Etched, which is building some very cool chips that he will tell us a little bit about, but I think more of it will be about just the general trends and how semiconductors work and all that. I'll leave it to Gavin.
Awesome. Thank you, Ben. As you said, I need to go promote the company a little bit at the end, but really I want to go talk about what the next 100x in compute looks like. And I want to go build some intuition today for how do chips work, and how does this actually influence the way we should build our AI models to take advantage of the trends in chips and not fight with them. And I also want to go address what I think is a practice of terrible teaching of the way that computers work, where I'm sure everyone of you knows that computers made up of logic gates and of transistors connected in some fashion or another. But what does that mean? How do we actually turn logic gates and transistors into a thing we can send to TSMC? What do you send to TSMC? What is TSMC? And that is what I want to talk about. So hopefully by the end of this, you can walk away with some framework for, all right, I understand how you could build chip design software. I understand the basic principles here. And as part of this, please interrupt. Please ask questions during the talk. I vastly prefer that to doing it after. So with the preamble out of the way, for this talk, we're going to break it up into 3 sections. How do chips work? How have their designs changed over the past 40 years? And okay, if we extrapolate a little bit, how should we build our AI model to take advantage of this? We'll connect back at the end. And the first question, how do chips work? Show of hands. Who here has heard of Apple, NVIDIA, AMD, Broadcom? You know what all these chip companies have in common? They don't make chips. None of them. These companies design the chips themselves, like NVIDIA building their H100, and they outsource the fabrication to another company and have, with the exception of AMD, for their entire history. And now, why is this the case? Transistors are not just switches. That's the way that it's usually taught. But in practice, transistor transition functions look much more like this. A 3-dimensional graph of the gate and the source voltage. Then you have to think about, oh, it's more complex too. Transistors leak a lot. Transistors aren't always manufactured in the same way. Some move faster, some move slower. That's going to screw with timing. They depend on temperature. As they age, their properties change. And it's always a little bit shitty, but predictably so. So what happened? All these companies decided that instead of paying for the R&D to deal with this graph themselves, they were going to outsource to Taiwan Semiconductor. And I want to go emphasize first the scale of how big TSMC is. TSMC is one of the largest 10 companies in the world, and all they do is manufacture chips. They design nothing. You send TSMC a file with your various mask layers. We'll talk about that in a second. You pay them $15 million, and then through their shitty web portal, you get your chips back 4 months later. And they spend an inordinate amount of money to develop the processes to go turn your design into chips. They can put that into perspective. You normally think of space flight, defense, these as a capital-intensive industries. But the capex of TSMC, the amount of money they spend to go build out their fabs, is 3 times that of Boeing, Airbus, SpaceX, Raytheon, Lockheed, all combined. Semis manufacturing is a massive industry, and because it is so expensive, all the companies you've heard about outsource it to TSMC or to Samsung. Now, okay, what does TSMC actually make? Well, inside of a chip, we have a number of layers. On the bottom, we have the transistors that you know and love. Again, we'll talk more about them in a bit. And on top of that, you have metal stacks. And if you were to go take this and rotate it so you can see it from the top, and we'll do that later in this presentation, you'll see that each of these is like a 2D image, showing where we have metal and where we don't. Same thing for the transistors themselves. There are wells for N-type things here, but not in all places. So if you turned it flat, you'd see a bunch of stacked 2D images. And these are what you send to TSMC. A literal thing called a GDS file It's kind of like an image of where do I put these and that and that and that. Just 24 or so stacked 2D layers. You upload them to the little shitty website, pay your money, and you're off to the races. Now, second thing here, to keep costs low, because it costs so much money to go develop these processes, most chips are built in very similar ways. That this metal layer stack up here changes a little bit, but the core is always the same. For Apple chips, NVIDIA, Broadcom, transistors on the bottom, a few very delicate metal layers that are expensive, and then some big coarse ones on top of that. So, okay, we have microchips. It's a big industry. They're all outsourced to one company that requires you to go do designs like this. With this, we have transistors and metal layers on top of that. Great. And these designs, these 2D images, can be extremely complicated. Way back in the 70s, people would actually hand draw these on big pieces of paper. Here's where we're going to have metal, here's not. Here's what connects to what, here's what doesn't. And I don't know if you can go see this all the way in the back, but here is an image of the Zilog Z80 microprocessor from 1976, where each one of those layers got drawn by hand, and they stack up all the layers and on the semi-transparent paper, view them from the top, and decided to go check design rules. Some guy would go in with a little compass to make sure that every one of these things followed the design rules. No wire was too close. And this kind of works. But as you go from things that look like this to things that have 80 billion transistors, it doesn't scale. And it also goes back to what we talked about at the beginning. Transistors are really, really complicated. And if you have 80 billion of them, they have to be extremely reliable. And there can't be very much trial and error, because each one of these trials today costs tens of millions of dollars. We need something better, a new primitive from which we can go build our modern chips. And now we have this in a thing called the standard cell. You've all heard of transistors are made up of, that computers are made of transistors, but also and or not gates. And the actual truth of the answer here is that for and, for or, for not, TSMC will give you things called standard cells, a little picture you can go project onto your big drawing that will compute and or not or inversion. And there are a bunch of these, and they come in hundreds or many, many different variants here. I'm showing here 3 variants of an inverter. It takes in one wire, it outputs the opposite of that. And this is a 6-track, 12-track, and 9-track cell. The difference here is how big those transistors are, and that determines how much power and how fast the thing switches. So if we're doing some cheap design, we'll use the small one. If we're doing something that requires very high performance, very high drive strength, we'll use the bigger one. And usually a design will pick only one of these. Now, how do these things work? We're going to go all the way to the bottom and then back up a little bit here. We have 2 kinds of transistors, P-types and N-types. And all we need to know is that for N-types, they carry current when the gate is high. So that means that, see that little metal prong in the middle there? If we raise that to 5 volts, then this will begin to conduct. And opposite true for the P-type. The P-type conducts by default, but if we raise the metal thing high, then it stops conducting. And we can go make these very cheaply. So let's take one more look at that NOT gate right here. We have, in the green region and in the red region, a P-type and an N-type doped region. The red line in the middle is the gate. This controls if they're on or off. And on the top, we have a high voltage 5-volt line, for example. On the bottom, we have ground. So our input is going to come in through that little blue dot there and into that red line. So if we put in a high voltage, then okay, this comes in. That top transistor, because the red line is on, is going to turn off and stop conducting. And the bottom transistor, the red one, is going to turn on and start conducting. So current will flow through that red thing and out to that blue crossbar on the right. Makes sense? And because that bottom row is ground, this is going to go force the output to be ground as well when the input is 5 volts. So 5 volts is turned off. And the same thing's true if we turn off this red bar. In that case, the red line will stop conducting, and the green line will start. The line at the top, the metal there, again, is charged to 5 volts. So that will flow through this green part and out. So when the red line is off, we go and turn the thing on to 5 volts. Does that make some sense? I'll stop for a moment to see if there are any questions. Awesome. So great. We have an image that we can go project onto our wafer that will go compute not. And this standard cell, we also have them for AND, for XOR, and so on and so forth. And for 4 input AND, 4 input OR, there are a huge number of these. And if you look at an actual chip itself, it's made up of many of these. The reason why we call them standard cells is because they're all the same height. You see those blue bars on the top and bottom? The high voltage, or these 5 volts and ground? We just chain them all together in a big row where we have some inverters, some AND, some OR, some SRAM, and so on and so forth. So great. We have these rows, we copy these building blocks in, and then with the metal, we can go chain the inputs to the outputs together, however our circuit describes. So the thing I want you to take away from this is that for every one of these gates, there's an actual standard image, standard design, that we're going to go copy and paste onto the big chip drawing. And then when we send it off to TSMC, because they guarantee that this will compute not correctly, we can be very confident that, okay, the thing we built on top of this will also compute the full drawing correctly. So okay, there's a basic principle. We're going to come back to that later. Ben.
Excuse me. One question for you. So
Shoot.
You said a little bit earlier that most designs only use one size of the cell.
Yes.
Like 6T or 9T or 12T. I'm guessing that that's because you need to have consistent spacing between your wires that are running the rails. But I'm curious, like, I understand why within a row you need that to be the case, but couldn't you have different rows that have different spacings of cells?
You totally could. You totally could do even more than that. We could have L-shaped pieces that we tile together in very complex structured designs like this. But the tools don't support it, so it doesn't happen very often. And you might also say, Gavin, well, if they were weird shapes, it'd be hard to fit them together. Don't worry. Hard to fit them together anyway. And this drawing here, this is kind of a toy example. But in a real chip, only about half the spots are filled. Because it's very hard to go wrap these things densely together, because we don't have very many wires to connect these.
Are there any benefits of using different sizes?
Oh yes. If we go back here, then a transistor can only pull and move so fast, and making it bigger allows it to go drive more things down the road. So, for example, a small gate might only be able to go control the inputs to 4. One gate might be able to control the inputs to only 4 others, and that might not be enough. But a bigger one will be able to go drive more. And same thing for the amount of power they draw. That a bigger one will have different power characteristics. Depending on if we want high power or low power, we will choose which one of these designs to use. Awesome. So now, one other thing, we gotta clock this. For all the gates in this chip, they need to go change state pretty much in sync. So we're gonna go drive a signal to all of them to tell them when to move and when to go advance one step. We'll just have one wire forking out across the entire chip with what's called a clock tree. That goes high, low, very easy. And the way to think about this is, all right, we have some syringe. We're pushing high pressure, then low pressure, high pressure, low pressure, high voltage, low voltage, and so on. But this happens very rapidly. A modern CPU runs at 3 to 3.5 gigahertz, 3 to 3.5 billion times per second. Cool. So, with that in mind, we talked about earlier, density on these is remarkably poor. You are not going to be able to fill every one of these boxes with a cell in real life. And even more than that, the parts of your chip that do math are only a tiny fraction of those. For every transistor, We need many more to go feed the data in just the right way, and many more to go do arbitrations of who's going to access this thing first. So in practice, on a chip like an H100 GPU, only about 5% of all the transistors on that chip are used for doing matrix multiplication, the actual floating point math itself. Way, way more are used for doing who's going to read this part of memory, how are we going to talk from one side of the chip to the other. It takes about 50 clock cycles to talk from one side of 800 to the other side. It is non-trivial. So, that all makes sense. There's logic. What about memory? Any one of these gates that we said is going to change its output based upon the inputs. This will make it challenging for us to go build things that remember their state. One option is for us to go build circuits that kind of loop back on themselves. This happens. It's what they call SRAM. But it takes a lot of transistors to do it, usually 6. And they are very, very big, taking up a lot of space on our die, and very leaky. They draw a lot of current, even just to maintain their state. A better idea is to use a tool called a capacitor. I imagine most of y'all are familiar. Where a capacitor can go store charge. Imagine, if you will, a water balloon that can be either full of water or not. And whether or not it's full of water, or whether it's not, will determine whether or not that bit is a 0 or whether it's a 1. And we can kind of tie it off and leave it there for a while, and it'll do just fine. Importantly, capacitance is proportional to the area of the capacitor. So, bigger capacitor, more capacitance, more charge you can store. Smaller, and the reverse. And in practice, here's the full formula for what capacitance is. We don't get to play with the D very much because the other thing for charge is voltage, and they're kind of inversely proportional. So our biggest knob for how do we get more capacitance is just to make the area bigger. Keep that in mind, because now we have to talk about, okay, how do we connect all these together? We have many capacitors. We have some capacitor, as shown on the image on the left right here. But we're going to have a lot of these. And we don't want to have a million wires running out from here to our main CPU. We have to find some way to only selectively read parts of this. So for every capacitor, we're going to have a transistor, a little gate there too, that will control whether or not we're going to let the capacitor discharge and flow out. So when we want to go read the capacitor, we're going to turn the address word line on, and that's going to connect the capacitor to the main bit line. So then we can just check, is the bit line high or is it low? What's the state there? Because that state is going to be whatever the capacitor was before we read it. And if we want to go change the state, we can just go change the bit line right there. So set it to 0. In that case, it'll draw the charge out of the capacitor, and we can then turn off the address word line to kind of lock that state in. Now, to go build this on a much larger scale, it works like this. We have a big grid of capacitors, millions or billions. And we have these rows of word lines and column lines. And whenever we turn on one of the column lines, it's going to kind of open up all the gates. So that whole column is going to be allowed to discharge their capacitor value onto these output lines right here. So if we want to go read, say, the 4-bit word on the left, we set that one to be high, and all the capacitor charge flows out. Only one problem. All that capacitor charge flows out. This is inherently destructive. So we need some way to fix this. And what we do is, when we're doing this read, we check to see, is it a 0 or is it a 1? Is a little bit of charge flowing out or is it not? And if charge is flowing out, then we go pack a huge amount of charge right back inside of it. So we have a big amplifier on the other side, looks for a small blip in charge, the capacitor discharging, and then when it sees that, crams way more charge back into the other way. And I have a graph here of what this looks like. When we want to go read from this, the output here is shown in blue. Initially, if the bit is in fact a 1, we're going to see that rise a little bit at time 1. And then our sense amplifier is going to see it, and then push way more current into that. And then we can go lock off the bit now that it's been refilled with charge, and we're good to go. But the main thing that I want you to take away from this here is that we are storing the charge in capacitors, and that for a capacitor, we need that charge to be used to raise that bit line up. The amount of charge we can have is proportional to the area. So less area, less charge, less ability to go raise the output to be high. And last piece in this preamble here, manufacturing. I know Ben talked about this a while back, but there are some layers in the chip that are very fine. They have to be made on big, expensive EV machines like the one on the left. Today's generation sell for $180 million a piece. The new ones are going to sell for more than double that. But not all layers have to be made on the big, expensive machines. The high layers are made on cheaper, what they call immersion lithography, deep ultraviolet, that are extreme ultraviolet machines. And these only cost a mere $40 million and have better throughput characteristics and break less often than the EV machines do. So whenever possible, we want to be on the coarser, cheap DV machines than on the expensive EV ones. So there is my full preamble. We understand we have a clock. We understand we have capacitors. We understand that, we can only make these things so small, or else we have to go pay the big EV tax. How has this changed over the past 4 decades? Well, the first thing to realize is that the industry counts on chips getting better. That is the reason why AMD and Intel and all the other design companies are able to get recurring revenue. New chips mean it's uneconomical to run the old ones. So there are strong, strong forces to go make sure things keep improving. However, you do occasionally hit upon physical limits. And one of them happened in 2005. Remember how we talked earlier about the clock that's going to push and pull to make sure everything syncs up in time? Up until around 2005, we made CPUs better by running the clock faster. That means more instructions in any given unit at time, and that was made possible by the fact that we were cramming the stuff closer and closer together, so the delays between one thing talking to another transistor were very short. But if you think of a syringe metaphor, then it's very easy to go pull and push the syringe slowly. And as it gets faster and faster, you need to go push more effort on it. And there's a point where if you want to go pull it in and out 4 times a second, it's going to take a huge amount of energy to go force the air in and out so quickly. And the same thing is true of clocks, actually, for CPUs. That up till around 3 to 4 gigahertz, the speed and the amount of power that a clock draws is pretty constant. Double the clock speed, then double the amount of flipping of the gates, so double the amount of power. But after around 4 gigahertz, it suddenly becomes way, way more power intensive to go feed this clock in faster and faster. And again, if you go to 5 and 6, it becomes totally impractical. A few folks have done it, but usually, if you want to run your CPU at 8 gigahertz, you have to go coat it with liquid nitrogen and do crazy cooling stuff to make the thing not immediately combust. Now, this was not economical. This was a serious threat to chips continuing to get better. So, what did they do? Did they keep pushing? Did they give up? No, of course not. We built multi-core CPUs. If we can't run one CPU faster, if that's going to be stopped at around 3.5 gigahertz, well, I'll have 2. And they did this, the core duo. It was very hard to program. People had to build all applications to be able to run on more than one processor at a time. But it happened, it hurt, that was life. And now modern CPUs have 8, 16, 128 cores. And this change kept progress going. If you look at the number of transistors on state-of-the-art CPUs over time, it's been pretty much exponential according to Moore's law. And even when the clock speed, shown in green, kind of tapered off, the number of cores began to rise to pick up for it instead. So because chips have to keep getting better, when one of these avenues fails, we will look for another one. On that topic, let's talk about logic. To go power this, more and more transistors on every chip every year, we had to go make them smaller and smaller and smaller to fit in the same amount of area, as you would expect. But it is getting harder and harder to make transistors smaller. And here's why. Remember how we talked about earlier? We have this NOT gate right here, where we have these transistors, the P and N types on the top and bottom, and they control with the gate whether or not current flows from the left to the right. The way this looks, if we are to visualize it in sort of 3 dimensions, is we have this gate shown in green that's going to control the flow of charge, and then either side, source and the drain, are on the bottom. And as this thing gets smaller and smaller and smaller and smaller, the amount of, well, the ability of the gate to go shut down the flow begins to decrease. It begins to get leakier and leakier and leakier. And at some point, around 14 nanometers, it becomes so leaky that the chips are going to draw too much power even just sitting idle, and they will combust. We have to go find some new way to make the gate grab the source drain thing a little bit tighter. And this is what happened. We moved to what's called FinFET designs, where now the source and the drain kind of flow through the gate, which allows for much more surface area between the gate and the source and the drain. That much more surface area allows us to go stop the flow of charge much better and make things that are less leaky. So every computer that you've had that's been built in the past 10 years has probably used FinFETs. Except now, with modern 3 and 2 nanometer nodes, even this is insufficient. As we get smaller and smaller and smaller, even this becomes too leaky, letting current flow when it's not supposed to. So what do? Well, we've gone to what's called gate-all-around transistors, where you don't have the same thing, the source and the drain, but the gate wraps around the entire piece for much more surface area still. And this is going to keep happening. Eventually, this will stop being enough, and they'll do nanowires or some other crazy thing to ensure that we keep getting smaller. But while we are making progress, things are slowing down. It used to be the case that every 18 months, the number of these on a chip would double. But now, TSMC expects a doubling in 5 years, between 2025 and 2030. Progress, but just not as fast. So that's bad. But for memory, it's even worse. Remember how we talked about before, that to go and do these memory arrays, what they call DRAM, we need a lot of capacitors. It turns out that capacitors are way, way bigger than transistors. So here's a cross-section of some memory taken with an electron microscope. All those circles are one of the capacitors, and the transistors themselves are much, much smaller, but you can't see them because they're below. Why is this the case? Why can't capacitors get smaller too, if transistors can? Well, remember, we need the capacitor to have enough charge to be able to go raise that line up a little bit, so that we can go detect that small little rise, and then push way more current back through it to go reset the capacitor. But because the total amount of charge a capacitor can store, proportional to its capacitance, and of course then to its area, making them smaller makes them able to store less charge, which makes them less able to go raise this bit line from 0 up to a few millivolts above, a few tens of millivolts above that. And because there's some inherent
I was going to ask, can we compensate for that by finding some really good dielectric to put in between the plates?
Yes, and we do, a little bit. That there are many other things we can do to make the area bigger. Like, for example, we can go make these way deeper, what they call deep trench capacitors. That's going to increase the surface area too. We can find a better dielectric, and we have people replace those materials like every couple of years now. But it helps, but not very much. And I'll get to that in a bit. And again, you might also be able to say, well, can we deal with a smaller voltage bump? Not really. Unfortunately, voltages in a chip are pretty noisy, varying by single digits to tens of millivolts. And I have the ideal graphs on the left and right, but in practice, as shown in the graph on the top right, it's going to shake a little bit. So unless this can consistently be higher than whatever the noise is, we're not going to be able to reliably read the bits. And it's not some one-off error, where there's, oops, sudden spikes in voltage we can go correct for with some error-correcting code. Now, the moment that this dips down below the noise level, we're going to get huge, huge error rates that are going to be uncorrectable. And for this reason, it is really hard to make the capacitors smaller, because smaller would mean less capacitance, which would mean less ability to go to determine that voltage switch or not. I have here a chart of the size of a bit cell on DRAM since the 1980. It used to go decrease pretty linearly, but then we got to a point where suddenly, oops, we need this area to have enough charge in the capacitor to go raise that bit line up. And we can't really do better than that. And this has actually caused a plateau in the amount of memory we can go fit on these cells. If you compare, for example, the NVIDIA V100 GPU to the NVIDIA V200, to the A100, to the A200, to the A3, to the H100, to the H200, the amount of memory, DRAM memory, on each one of the HBM dies is the same. It's remained 2 gigabytes per layer. Now, that's not to say that folks aren't clever. The amount of memory per layer has remained the same. Well, what if we just stack more and more and more layers? And they do, and it kind of works. But of course, the more layers in the stack, it's harder to go dissipate heat. It means much more costly memory. Already now, on H100, the cost of the memory is double that of the chip itself. Now you have just way more silicon area in the memory cells than in the die itself. Any questions here? Did I see a hand?
Could you clarify what you mean by cost being higher?
Yes. Let me skip forward a little bit here. So what we do here, to go and accommodate for the fact that, well, we can't actually fit more capacitors on a single die, is we're going to stack them into 4 high stacks. And they had a name for this originally called HBM. And then, of course, years went by. They weren't able to fit any more memory on this too. So they stacked them even higher. Now, 8 high. And now 12 high and 16 high are coming onto the market. And with these stacks, well, the amount of silicon proportional to the size of each one of the dies times the number of dies. So a 16 high stack is going to cost 16 times more than a 1 high stack. So even though per square millimeter of silicon, the memory is a lot cheaper than the compute die itself, because we stack these dies 12 or 16 high on modern chips, the total cost of all 16 of these is going to usually exceed the cost of the raw CPU or GPU itself that's talking to this memory. Make sense? Awesome. So that brings us again to all progress now is really just stacking more and more memory. And while occasionally we get bumps in the capacity per layer, it is not the norm. That's why you've seen the A100 and H100 be 80 gigs apiece, although the new B100 that's coming out next month is going to have a little bit more. Second thing about this, remember how we said earlier that there were some coarse metal layers that were cheap to manufacture and some fine ones that were expensive? Well, as a capitalist, looking at these capacitors themselves, we might think, hey, if the capacitors aren't getting smaller, then why, oh why, would I pay for fine metal layers on here? Why not use the coarse old machines to manufacture the metal layers on all of these? This would be bad. This means that we can't really manufacture the memory cells and the actual compute blocks on the same node anymore, because compute needs the advanced EUV machines, and memory can't really use them because it wouldn't be economical. So this constraint requires us to go separate out the memory dies from the logic die. But that's okay. That's the way that the H100 is shown there, and the AMD GPUs, and the Google TPUs, and Trainium work. So because memory is not getting better, we can't use the very fine we can't use the very fine patterning machines on it. And because we can't use the fine patterning machines on it, but we have to for the logic, we can't build them on the same process. Inherently, because capacitors aren't getting smaller, we must build logic and memory on separate pieces of silicon and glue them together afterwards. So, hopefully, with a few of those examples, that gives some intuition for how does the design of the way these standard cells work influence the way these trends are being shaped? When we saw that clock speeds weren't going up, because you have to go push that clock in faster and faster, we moved elsewhere to multi-core. And now that we're seeing memory stop advancing as fast, what does that mean for our compute? Now that we're seeing transistors kind of slow down a little bit too, what does that mean as well? Well, first, demand for compute is still very much going up. And costs are still coming down. I'm sure you all have seen the charts of the sizes of models over time. We've gone from GPT-2 with 1.5 billion, GPT-3 with 175 billion, now GPT-4 is rumored to have 1.8 trillion parameters, and we are not stopping anytime soon. And so, to deal with this, we should not fight physics. We should not demand denser and denser memory. We should instead be able to be clever and reuse that memory load way more times. Instead of requiring the transistor to go keep shrinking faster and faster and faster to go keep pace, we should ask, hey, we're only using a very tiny fraction of that die for the math blocks anyway. Maybe we can go add more math blocks per chip, the way that we added more cores per CPU. We should ask, hey, maybe we don't have to go store a copy of the inputs on every one of the chips. Maybe there's a better parallelism strategy that will let us have more compute per die, a thing that does shrink instead of memory itself. And that brings us a little bit to me plugging my current company. There are many trends in chip design. At Etched, we're dealing with just one of these. We're building very specialized chips just for transformers. It turns out that by building a chip that's only for one category of AI models, just transformers and just inference, you can fit way more compute on the silicon. Earlier we talked about how you had to pay the overheads for networks on the chip and figuring out who can access what memory and figuring out, okay, how do we do instruction decoding and so on and so forth. But if you're willing to just pick one single kind of model and burn it into the silicon, more than 5 times more of the chip can be spent on the raw math blocks. And you can get 5 times more compute per die. And I think this meme sums it up pretty well. That, yes, it's true that flops are not everything. And yes, it's true that memory is a factor and that Moore's law is slowing down and that we could do sparsity and other things too. But the fact is that just like the people building CPUs had to pivot to multi-core, now that memory is slowing down or almost entirely stopping, and transistors are still getting better and better and better, we should return to this old paradigm and build models that will use the more flops, even if memory advances slower. So, that is my talk. I'm Gavin. We are very much hiring at Etched, so if these kinds of problems of matching the model architecture to the silicon get you excited, please come talk to me after this. But I want to go leave the rest of the 20 minutes here for questions. Thank you. Ben.
I'll go. So in this talk, you focused very much on the memory itself in terms of it, and a little bit less on the I/O and the bandwidth.
Yes.
So I was wondering if you could talk a little bit about how bandwidth and potential trends in terms of how we may get more bandwidth on the chips relatively soon. How does that change the equation here?
Yeah, sure. So, while I've talked about how capacity has not changed that much, bandwidth to memory has very much increased. That we've gone from, I think on original HBM it was about 2.4 giga transfers per second. That's now going up to about 9.6 on some of the newer chips. And additionally, if we go back a bunch of slides, I have at the top left here an H100, and I have on the top right here a NVIDIA MI300X. And you'll notice that MI300 has 2 more of those memory modules than the H100 does, 8 instead of 6. So that's another trend that people are seeing, that you can go and add more of the chip together on a single package to go make the full thing a little bit faster. You work around these limitations of Moore's law and capacitor scaling. For I/O in particular, we haven't talked about the ability to get data out of the chip and not. That's actually advanced quite a bit, and probably will continue to do so. Right now, most chips use 124 gigabit, what they call serial and SerDes, serializers and deserializers, and that's pretty proven technology at this point. 124 gigabit SerDes have entered the market on time, and now a number of companies are interested in what they call co-packaged optics, where you go and connect optical fibers onto the chip to get better and better interconnect bandwidth. It's hard stuff, but I do think it's going to work out. Synopsys and Cadence have built optical design tools that kind of work. So I think in the next 10 years, we will see GPUs that have co-packaged optics for better interconnects from chip to chip. Does that answer your question? Any other questions here? In the back.
Yeah, I just have a question about like your thoughts on the future. So like right at the end, you were talking about like having a specific chip for like doing inference. I'm wondering if you think that like in the future we will have like specific chips for training, for inference, for all these other types of AI applications.
Well, I think it's even worse than that. As time has gone on, these models have gotten bigger and bigger and bigger. And additionally, they've gotten more and more and more and more expensive. If we compare, say, GPT-3, which cost 10 million to train, with GPT-4, that cost 100 million. And now Anthropic's next-gen models are going to cost 2 to 3 billion to train. We are seeing that every 2 years or so, the cost of the leading model goes up by a factor of 10. And while the cost of making a chip is rising year over year, it is not rising nearly as fast. And we've gotten to a point where the cost of a leading model is way, way higher than the cost to go build a whole new chip, a whole new design from scratch. And what I think this means is we're going to see individual chips for individual models. When, say, GPT-7 is trained, it is going to run on a chip that is only for GPT-7 inference. That'll be expensive, yes. It's a $100 million project. But compared to the cost of training GPT-7, it is a drop in the bucket. And there is so much performance to gain by building a single chip for a single model. Because only 5% of the total transistors on here are 4 math blocks, and we can make that much bigger, like 30%, by specializing on a single model architecture, you end up with a gain of more than an order of magnitude by specializing on a single model. And that's what we're doing at Etched. We are for only transformers. It is a very targeted bet, which has a lot of risk, but that allows you to get a pretty massive performance improvement. And while we may be early, we will eventually be right. Anything else? Shoot.
Could you tell us about some of the challenges that come with like building your own custom chip? I'm guessing there's no infrastructure available for like kernels or any other program. So what are the difficulties that come with building it all from scratch?
Software is extremely hard. I used to work for a couple of AI compiler companies, and while most people think that software is very hard, I now believe it's almost impossible. But we have a great advantage at Etched in particular because of how specialized we are. If your chip only does one thing, you don't have to go write kernels in the same way. It only does one thing. It can't be programmed. Much like a Bitcoin mining chip does not have to be programmed to mine Bitcoin, a transformer-specific ASIC does not have to be programmed to go run a transformer. And this makes the software problem much, much simpler. That said, for other chips like AMD GPUs or the TPUs as time goes on, they still have problems of having to go write their own kernels. But as model architectures get more and more consolidated, transformers are all pretty similar. After all, the amount of kernels you have to write goes down. And for a thing like GPT-4, you can even probably get away without doing a totally automated compilation. It's okay if it costs an engineer a couple of months to go write the code and import the GPT model from NVIDIA to AMD Silicon. That's not cheap, but compared to the cost of the model, it's just not that much. So I think that this trend of models getting bigger and more expensive will not make the switching costs any higher, and as a result, the fraction of the switching cost versus the total cost of the model is going to go down. making hardware more of a fair fight.
Well, what you say makes sense from a cost and money perspective, but the field is also moving faster and faster and faster, and hardware cycles are a little bit slower than AI, development cycles. So, do you have thoughts on, is that going to change? Are we going to see faster hardware development cycles, or?
Well, this is totally true. Hardware development takes a very long time. NVIDIA, AMD, and Intel ship a chip every 2 years, which is pretty good, but it masks the fact that they plan these well in advance. When they had the H100 going, and when they shipped that, they had at the same time the next chip, the B100, and the next chip, the R100, and the next chip, all in development at that same time. So it takes a long time to build chips, much longer than you might realize. That is a real risk of building over-specialized hardware. It's bitten folks in the ass before, but I do think that model innovation is not quite at the speed that it once was. If we flash back, say, 6 years to when we were having new RNNs, new LSTMs every year or two, we've now kind of stuck around on transformers and that core building block for a while. If you compare GPT-2 to, say, Llama 2, yes, we now do query attention, a new kind of positional encodings, and a new kind of norm that we moved across. Now we have a second one at the very end of the model. So there are small changes, but the core of dot product attention, the core of the feed-forward blocks, those have remained remarkably consistent. And now you're even seeing innovations like, for example, speculative decoding, or innovations like Google's ability to do a little bit of chain of thought tree search, look ahead in a few directions and pick the best one. And these are built on top of transformers. They don't work nearly as well on, for example, LSTMs or RNNs. Because for an LSTM or an RNN, you have to go recompute the intermediate states for every one of those branches you want to look down. You have to go store a huge number of intermediate states at the same time. Whereas for a transformer, you can just have a single line of the KV cache that you discard after very cheaply. So that's a lot of thoughts. My broad answer to this is yes. There is risk of over-specializing. This is a scary bet right now, what we're doing here at Etched. But the pace of progress is slowing down. Folks are building on top of the transformer rather than trying to replace it in many cases. But good question.
How do you compare what you're doing to Grok?
The folks at Grok are smart people. Grok in particular does not use the memory that we talked about, what we call DRAM memory. They looked at this and said, hey, it's really expensive. This would more than double the cost of the chips. So instead, we're going to have almost no memory on the individual chips. Just the SR memory where we have the gates looping back on each other. And as a result, they have way less memory per chip. While a GPU will have about 80 gigabytes, a Grok chip has about 200 megabytes. So literally 400 times less memory. And this means that to go run a model like Llama, you have to chain a huge number of chips together. And they do. To build the demo that you saw on Twitter, it took 576 of their chips, all working together, all reading from SRAM. And they compare that to, say, 8 GPUs, and they say, we win. We're a little bit faster, 2x better. But of course, if you compare 500 GPUs, 500 of the Grok chips, the GPUs will dominate. And some of the other competitors are now working on their own GPU-based versions that have, say, 32 GPUs. And in the next couple of months, you'll see some of those ship, and they'll be faster than the Grok implementation. So while Grok's doing cool stuff, this idea of not having capacitor-based memory, I don't think works very well in practice. No one does it. Google doesn't. Google uses capacitors. NVIDIA, AMD, Amazon, you name it. I don't think it scales.
Earlier in the talk, you talked about how memory bandwidth is still improving, and general intuition is that a lot of workloads are actually memory bandwidth bound instead of compute. So how does putting more compute on the chip help? And then, what are also the challenges you have as you add more compute to the silicon?
So first, yes, this is a very good question. Memory bandwidth is still getting better. And we haven't talked about it now, but there's going to be a new generation of HBM called HBM4 coming out in about 3 to 4 years that will double the number of wires from the dies, from the memory onto the chip. That said, the cost of having this memory, the capacity, is very much still going to be an issue. So while there are things that are compute bound, and while there are things that are memory bandwidth bound, this is only kind of a band-aid on that. That memory bandwidth is still as well slowing too. If we compare from 10 years ago or so, we've gotten about a 3x improvement in HBM bandwidth, which is good, but not as fast as we have seen logic improvements or compute improvements. So even if the rate of progress for memory bandwidth does continue to increase, it will still be slower than that for compute. So I still believe that more compute-heavy workloads will be able to better utilize the chips in the future. Any final questions? Shoot.
So Ben was asking earlier about memory bandwidth. I was wondering, so you have like a memory controller in between the compute units in the memory.
Yes.
What does that look like? How does that work? Because I'm assuming it has to like access every single cell of memory somehow. Are there just wires to all of them?
Also,
Talk more about what a memory controller would be.
I'll nerd out a little bit here. That inside of this, we have the compute die, we have the memory. But if we go a level deeper, inside of the compute die is made up of many different parts. What we have is a PHY and a controller, where the PHY sends the physical signals through this interposer layer that connects the two together to the memory stack, and the controller tells it what signals to go send. Same thing on the other side here. Logic die will go decode these and send them up to the stack. There's a second problem, though, that we haven't talked about. Earlier in the talk, I was saying that everything here leaks a lot, and so do capacitors. If we leave one of these capacitors alone for, say, 100 milliseconds, it will lose all of its charge. We won't be able to tell whether or not it had a 1 or a 0 or not. So to solve this problem, we do what's called refreshes. Internally, on every one of those logic dies, we have little clusters of these bit cells, 10 million or so. And for every one of the clusters, we have some old transistors that will go and read every one of those rows every 40 milliseconds, and write its value back with a new stronger charge, and repeat that process again and again and again and again. So there are a number of controllers that are controlling these reads. Most of them are not visible to the total die over here. But occasionally you'll see things where if you try to read from a bit cell that's being refreshed, then there might be a very long delay where you can actually get your data back. And this can give some sudden spikes in negative performance. And now the logic dies on the bottom here are actually pretty smart. You can go tell the thing in advance, hey, I'm going to do a bunch of sequential reads. Don't refresh that memory when I'm trying to read it. Wait a little bit longer. And the chips are generally pretty smart on this. But I forget the question, I apologize. Yes, we have controllers on the logic die, controllers on the bottom logic die of the memory that figure out which part of the stack to read from. And then inside every one of these DRAM dies, there's logic on those too to go and control the little subsection that they own. So if I want to read from one patch, I'll send that one signal over to the logic die. It'll say, oh, it's on layer 3. I'll read from layer 3. Layer 3 will say, oh, it's in a subsection 109. It'll read from subsection 109, and we'll write that value right back. Ben.
Can you talk a bit about heat?
Heat. Heat is a massive problem for basically everything that you see in this picture. We'll start with the HBM DRAM dies right here. Each one of these generates heat because the capacitors are leaking, we're refreshing them, we're reading, we're writing. And as we go stack more, we get more heat. And taking heat out of the stuff in the middle is very challenging. And it's one of the reasons why there's been a real slowdown in the ability to go stack these microchips higher and higher and higher. The physical stacking is not that hard, but getting the heat out is challenging. So a lot of innovations now go into making the things leak less, consume less power, draw less heat. Same thing for the logic die itself. This as we get more and more compute on the die, we will see more and more of these transistors flip from on to off to on every clock cycle. Additionally, if we do the AMD approach and combine a bunch of these together, each one of those will generate its own heat as well, so more total heat for the system. And as a result, the power drawn by leading GPUs has gone up from 300 watts to 500 watts to 700 watts to 800 watts for the new MI300s. And with the new NVIDIA release, you will see it crack more than a kilowatt per card. So yes, heat is a big problem, and as these things get bigger and bigger, we draw more of it. Now, how do we solve it? We don't, we deal with it. You're gonna see data centers move to water cooling. Again, you'll see more of that next month. You're gonna see data centers move to delivering the power closer and closer and closer to these things because, well, more heat, more power. And additionally, there's one third trick that people use all the time. For a transistor to go change state, the amount of power that it draws is proportional to the square of the voltage. So, cut the voltage in half, cut the power draw by a factor of 4. So if you look at the the voltage of the P to V to A to H100, it has steadily decreased. Now I think it's at about 0.8 volts for the chip. It'll keep getting lower. This also leads to problems of current. If your chip is, say, drawing 0.8 volts, but it needs to have a kilowatt, you have to go put in more than a kiloamp of power into this chip right here. And if you, say, do that from off the chip, there'll be big losses. So what do? Well, you used to go and power these things with 12 volts. But 12 volts, even that has to run at hundreds of amps to power the full system. So modern chips now have the wall outlet turned into 48 volts, and that's passed from the server to the chips themselves. On the chip, we down-convert from 48 to 12 volts, and we have modules. If you can see on the H100, they are the little chips on the side of the big one. That will turn that at 12 volts into 0.8 volts and pass that into the chip. And by doing the power in this clever way, we can be a little bit more efficient when we have to go pump the hundreds or thousands of amps in each one of these things. So yes, heat is a big problem, and there's not really anything we can do about it besides being better at cooling and being better at power.
A follow-up question on that is that right now the whole stack is completely CapEx dominated, not OpEx dominated. Do you think that might change as more competition enters the industry and the chips consume more and more power and that costs money, or is it like, are we going to be in a CapEx dominated world for at least the next 5 years?
Well, for the next 5 years, I do think it'll continue to be CapEx dominated, just because it's so heavily CapEx dominated right now. We can do some back of the envelope math. One of those H100s draws about 700 watts. So a watt's about $1 a year. Over a 5-year lifetime, that's going to be 3.5 grand in power. But the chip itself is going to cost 30 grand. So only 10% of the total cost will come from the power. And even if the things drop in price a little bit and the power goes up a little bit, it'll still be CapEx dominated. But I do think that eventually the margins on these products will go down by a lot. It'll become more similar to CPUs and to switches. And as a result, the cost will go down and it'll be more evenly matched. I do think we are at time, so maybe one more question and we'll call it. Oh, perfect. Any other questions here? Fantastic. Well,
thanks so much, Gavin.
My pleasure.
All right, well, even though I'm sure Gavin has work to do, I'm going to drag him to stay here for a little bit and talk to anyone who wants to talk to him. And I'll turn off the stream. Give me 1 second. Yeah, thanks again so much.
My pleasure.